In this video, I'm going to look at topic 2, electric fields and Gauss's law. So we'll get through some of these questions here. Which is a possible unit for electric field, so we can actually figure it out. There are two formulas that I remember for electric field that can help us find a unit. The first formula we used was FEC, F equals EQ, FEC. The other formula was VED, V equals ED, VED. Changing them for you, so that will become E equals F over Q. This one, that will just become E equals V over D. So this is the formula in terms of E. Putting the units in, F is force, that's in newtons, per Q is charge, which is coulomb. Newtons per coulomb, or V is volts, which is also V, per distance is meters. So these are the two units I'm looking for in the question. Voltmeter, that's multiplying, so that's wrong. Joule coulomb is not here. Joules per coulomb is also not here. Newtons per coulomb is here. So this one is here. So we can say D is the best answer for this. Over here, electric field lines, if you remember, they go away from a positive charge, they come out of a positive, and it goes into the minus. Okay, so keep that in mind. Out of a positive, into the minus. So it'll be from positive to negative, from plus to minus. That's how it works. If you have this and you're trying to find the net force acting on this, you have a charge, you have a field. Well, I've written the two formulas that are going to help us. One of them is FEC. We can use FEC. I'm asking for the force. I have named this formula FEC. 27 times 3. If you do that, you will get 8.1 times 10 to the minus 6. Over here, you have another negative charge and experience of force. Find the magnitude and direction of the field. So if I'm just going to find the field, I will just use FEC again. I'll do E equals F over Q. I'm going to take this and I'm going to divide it by this number, and I should get 2 times 10 to the 6. So A and C are wrong. Now, is it going to the right or going to the left? Well, let's find out. If I placed a minus charge here and I put him there and he is going to the right, the minus charge is going to the right. And if I had a field, now, which one is he attracted to? Well, he should be attracted to the plus side. And that means he'll be repelled by the minus side. If that's the case, the field goes from plus to minus, as we wrote up there. Plus to minus. The field is actually going this way. So the direction of the field is to the left. So that means B is also wrong. It must be D. You get the number by dividing the force by the charge, and then you get the direction by deciding which way he is going, and he must be attracted to the plus. If I put a positive charge here, he will follow the direction of the field because he's attracted to the negative. So that's a way for you to figure it out. Here we are trying to see the direction of generally a field is the force on a positive test charge. We use a positive, small positive test charge so it doesn't get in the way of the force and the field. And I think I've just given away the answer to the next one. Why is it a small charge? So it does not disturb the field. If you place a big enough charge in, it will disturb the field and ruin all your results. So it's not going to be any good for anyone. Which of these is true regarding field lines? Well, we know they start on the positive and finish on the negative. Yep. They never cross, that is true. They have their own line. The direction of the field is tangent to the field line at any point in space. What does that mean? Let's draw it out. I'll have a plus and I have a minus. I have a field going that way, and maybe that way, and maybe that way. So kind of curved. Maybe another one, and another one. And it's going into the minus. Out of the plus. Okay, so these lines never cross, and it starts from plus, ends in minus. And when it's talking about the direction of the field is tangent to any point in space, so basically if I picked a point here, the field at this particular point is going up that way. But if I follow it here, it's going that way. It's going that way. This is what it means by tangent. A tangent is a line going like in a straight line, like that. So that is the field at each individual point. If I was to pause it here, if I paused it here, it is going to the right. But if I paused it here, it's kind of going up a little. So this is a tangent to the curve, like that. Okay, so it's a little bit of math knowledge there. All right, moving on to the next question. We've got some more diagrams. Which of these are good? These should be really straightforward. And that's wrong because they're both plus, and they will not do that. This is true because they're plus, they will repel. This is wrong because the arrows are going the wrong way. And this is also wrong because the arrows are going the wrong way. They should be facing inwards here. Which of these is good for a single positive test charge? It must be coming out, so it must be this. Over here, what can we say about these? Which ones are positive? Well, you can clearly see that's coming out of the 2 and into the 3 and the 1. So this must be B. So the distribution here, we have electric field. What can we say about this? Well, we know A is plus and B is minus, and there's more lines here than there are over here. So I can say that A is stronger than B. A is greater than B. This is good. This means A is less than, this means equal to, neither of them. It is greater than B. All right. Next page over here. So what is this one? It is saying what's happening in these charges? Well, you can clearly see they're all pointing outwards. So they're all positive. So that is straightforward. Field lines should not be that difficult, hopefully. Using this picture, you can estimate the numbers. You don't need to calculate these numbers, you can estimate. I know this is plus. I know this is minus, and I know this is plus. So Q1 should be minus. So A is wrong, and so that leaves me with here. Q2 should be positive. Q2 should be positive, so that's okay. That looks okay. That means D is definitely wrong. So I have two options now. One is bigger than the other. So looking at this one, this is bigger than this. More lines, which means Q1 should have a bigger value than Q2, and which means out of these two options, B is the best answer. Q1 is 32, and this one, Q2, will be 16. That looks okay. This does look a lot bigger than this. That looks fine. This would be wrong because this is saying Q1 is only 16 and Q2 is 32. No, there should have been more lines on this side. There is not. Most of them are on that side there. So, assuming there's nothing else going on, which of these can represent an electric field? What's wrong with this one over here? This is very deceiving. You have an arrow coming in, but then you also have arrows coming out. So that's wrong. You have this one. This looks like a uniform field. Almost. It's kind of curved a little. This one is going in a circle, so this is not really going to happen. And this one here, these lines will be connecting each other. They'll be intersecting with each other. So that's not very good. The lines are not working out correctly. The best one will be this one here. So we would have maybe a plus on this side and a minus on that side. That's how this one would work. So 2 is good for us. And over here, we're looking at where it's the strongest. Well, they are clearly connected to each other. So the strongest is closest to the field lines. We will say E is the strongest in this case, followed by B, then perhaps D, and then after that you will have A and C, which are equal to each other. If this was repelling, then there will be 0 at E. They would cancel each other out. E would have the weakest field if they were repelling, but they're not repelling. And what I mean by repelling, so like for example these two are repelling, in between these two, right here, there is nothing happening. So keep that in mind as well for future questions. In this case, you're doing some more vector addition, which I did in a previous video, but I'll quickly go through some of it with you now. Again, 4 charges are located in the corner. You need to decide where the net field is at point P. So if I'm standing at point P, what is happening? Well, I know that according to point P, I have a plus 2. So I have maybe 2 arrows pushing that way. Because remember, it comes out of the plus in all directions. So at point P, it's coming out. Then, over here on the other side, however, look at that. I've got a plus 1, a plus Q. So that's pushing back that way by only 1 arrow. Okay. Let me just change the color here quickly. So this one and this one. This is minus 2, and minus points inwards. So this is trying to pull it in by 2 arrows. But this one is trying to pull it back by 1. you can see that I can actually cancel out some of these. I can actually cancel this line with maybe this line with maybe that line. I now have two small lines remaining. You can see these two arrows. Sorry that I drew them quite small. For me to find the resultant, I'll just take these two arrows. I can do tip to tail, and I will realize that if I do that, it's going straight down. You can kind of figure that out. It's going to go straight down. So that means we had two going down this way, but it was slightly cancelled by this one. We have two coming in this way, but slightly cancelled by that one. So once you've done that, you can realize it's going towards the middle of the bottom of the square. So this is the middle and this is the bottom of the square. So that means C would be the right answer in this case. Okay. Another idea over here. You've got three charged particles. What is happening at this point? Now, you can see that this is going inwards, this is going inwards, but this is pulling outwards, just like we did before. Even though this charge is doubled, the distance is greater. And that makes a big deal for electric fields as well, because E equals K Q over R squared, still squaring the distance, much stronger. So because these two are both closer, they will be stronger. The best answer here will be D. Then, using the same rule that we just mentioned, what would happen if I halved the distance? You will do the exact same thing. Remember, set everything to 1 except the thing I'm changing. I will say K. I know it's supposed to be 9 times 10 to the 9, but I'm going to call it 1. The Q did not change. I will call it 1. But I did change something. I changed the distance. The distance was a half, so I'll divide by a half squared. If you directly put that in your calculator, you will get 4, which means 4E. So that will help us with this question. Moving on to the next one. This is a charge. What is the field produced at a certain point? So you're just going to use the same formula, E equals KQ over R squared. 9 times 10 to the 9 multiplied by 4 times 10 to the minus 9 divided by 0.40. Remember, we cannot use centimeters, it must be meters. That's 0.40 meters. So that's what you would do here. Solving that, try it yourself. Using the same formula, you should get D. Over here in the next one, it is asking you for the charge now. So you're just going to use KQ over R squared. Same idea, E equals KQ over R squared. And we're just now going to solve for Q. So you can just use shift solve in your calculator. You have the E, which is 157. You, of course, have the K, that is already a given, 9 times 10 to the 9. And you have 0.40 again. Solve for Q. Shift solve, and if you do that correctly, you should get 2.8 times 10 to the minus 9. It'll take too long for me to write using this mouse, so it's gonna be very messy. So you're gonna have to do a little bit of legwork yourself here. So question 21. Over here, we're doing the same idea. We have this charge. We have this field. Where on the x-axis? Now I'm solving for R. Same thing. E equals KQ over R squared. Solve for R. We have 157. I have 9 times 10 to the 9, and I have 4 times 10 to the minus 9. So the minus 9 and the positive 9, they will actually cancel. Anyway, so 9 multiplied by 4, and then solve for R squared. That equals to 157. If you do this, you should get 0.48 or 48 centimeters. Okay, in this case, you are now standing at a position in this corner of the triangle, because two charges are here, so the only other place is here. There's the only other place that you can be, the third corner. You will calculate this one, and then do Pythagoras. We've done this many, many times before. You will do E, the first one, K, that's a Q, but that's a K. Q1 over R squared, that is the first one, maybe here. Then I will do E2 equals KQ2 over R squared, that is maybe this one over here. Once you've done that, you'll just do the square root of E1 squared plus E2 squared. This is just Pythagoras, that's all. Solving that, if you do it correctly, you should get 5.4. I'm going to stop that there because this video has been long enough.